At 300 kilometers per hour, air stops behaving like a soft gas. It starts behaving like a solid wall. When a standard vehicle moves down an open highway, it pushes surrounding atmospheric air out of the way relatively smoothly. But when a 450-ton steel missile enters a narrow mountain tunnel at 1/3 the speed of sound, everything changes. The oncoming train compresses the thousands of tons of atmospheric air trapped inside the tunnel like a giant piston in a syringe. When that high-pressure shock wave reaches the open exit portal of the tunnel, it cannot dissipate gradually into the surrounding environment. Instead, it expands violently outward into the open atmosphere, creating a massive, low-frequency sonic boom that resonates across the landscape. These intense shock waves were known to shatter nearby home windows, rattle residential foundations, and echo for miles through surrounding valleys. Back in the 1990s, this phenomenon wasn't merely a severe noise complaint, it was a physical barrier threatening the future expansion of high-speed rail. High-speed trains needed to slow down as they passed through tunnels to avoid generating the sonic boom and the damage this phenomenon could cause. Engineers realized that unless they could soften that initial entry wave, speed limits would remain permanently capped by environmental physics. The breakthrough didn't come from supercomputer simulations or wind tunnel tests. It came from observing natural biological systems. Engineers closely analyzed the Kingfisher, which dives from open air into dense water at high speeds without creating a splash. The Kingfisher transitions effortlessly between two fluids of radically different densities due to the specialized wedge-shaped profile of its beak. Japanese engineers completely redesigned the front nose of the Shinkansen bullet train to mirror this exact aerodynamic geometry, and found results were immediate. The new nose design sliced into the tunnel air gradually, reducing the entry pressure wave by an astounding 30% overall. The sonic boom vanished instantly, allowing trains to travel faster. But solving the aerodynamic wall revealed an even deadlier hazard beneath. If you inspect a high-speed train wheel up close, you will spot something counterintuitive. The wheel tread is not a flat cylinder. The surface of high-speed train wheels are actually machined into a subtle cone form, rather than the traditional flat form. When the train shifts sideways, one wheel rides up onto its wider diameter, while the other wheel drops onto its narrower profile. Because the one side now has a larger effective circumference, it travels slightly further per revolution, naturally steering the train back to center. This self-centering conical geometry is a masterpiece of mechanical engineering, keeping trains centered automatically without complex electronics. However, when velocity increases significantly, this helpful self-correcting mechanical feedback loop turns into a violent, destructive instability. In mechanical engineering, this destructive force is known as hunting oscillation, with the wheels repeatedly trying to find their natural position. Eventually, the kinetic forces become so intense that the wheel flange climbs right over the railhead, triggering a catastrophic high-speed derailment. To eliminate hunting oscillation, engineers added heavy hydraulic yaw dampers between the train body and the wheel bogies to absorb lateral movement. Engineers have paired these physical dampers with computerized active air suspensions that continuously sense and counteract micro vibrations in real time. Bringing a multi-hundred-ton bullet train to a complete stop from full velocity is a severe thermal management nightmare. If you rely solely on conventional mechanical friction brake pads at high speeds, that massive kinetic energy turns into extreme thermal energy instantly. If wheels lock up for even a fraction of a second, the steel rail acts as an industrial lathe, grinding flat spots on the wheels. To prevent this, high-speed trains use 3 non-contact braking systems operating together to bleed off kinetic energy without damaging equipment. First, electric traction motors are reversed into generators during regenerative braking. Second, non-contact magnetic eddy current track brakes induce opposing magnetic forces directly inside the steel rails to slow the train silently. And third, emergency roof-mounted air brake panels pop up into the airflow, using the force of atmospheric pressure itself to drag speed down safely. Even with aerodynamics, stability, and braking mastered, a fundamental physics challenge remains. How do you deliver megawatts of continuous electrical power to a machine moving faster than a sports car? High-speed trains don't carry fuel on board. They draw massive amounts of high-voltage electricity directly from overhead catenary wires suspended above the track. Connecting the moving train to this static power grid is the pantograph, a spring-loaded, carbon-tipped arm mounted to the roof of the carriage. At low speeds, keeping contact is trivial. But at 300 kilometers per hour, the pantograph carbon contact shoe slams into micro-imperfections in the wire thousands of times per minute. The pantograph pushes up against it while traveling at high speed, sending a physical mechanical wave ripple traveling down the line ahead of the train. That mechanical wave travels down the wire at a fixed speed. Its wave propagation velocity directly dependent on how tightly the wire is pulled and how heavy it is. Here is the danger. If the train speeds up until its speed matches the wave speed, it catches up to its own ripple. The pantograph essentially outruns the wire's ability to bounce back down into position. Because the wire stays pushed upward in front of the train, the pantograph loses physical contact with the copper conductor, creating a gap between the train and its power source. The moment that physical contact breaks, high-voltage electricity tries to bridge the gap anyway, producing a massive, ultra-high temperature electrical arc, cutting off power to the train. To solve this, railway engineers pulled the overhead wires under colossal tension, using heavy hydraulic systems and counterweights to pull with up to 30 kilonewtons of force. Tighter wires increase the mechanical wave speed down the line, ensuring that the ripple always travels much faster than the train can ever run, preventing the pantograph from ever catching its own wave. By mastering the balance between wave dynamics and electrical arcing, engineers keep high voltage energy flowing continuously into the train, even at 1/3 the speed of sound.